Hi.
Hello everyone. Hello Akshay.
Hi, Vedant. Hi, Tulsi as
Uh,
well.
Hi. How are you today?
yeah, we are great. So yesterday, what happened? Like Tulsi, you were not able to join again.
It's my laptop's Wi-Fi drivers. They're so bad. So every time I share my screen or every time I join some meeting from my laptop and I try to do something else, it just breaks and the internet connection goes down and stuff happens. I'm trying to fix it.
Okay, okay. So today, is it fixed or will Akshay
Uh,
will present?
Today, I'm actually gonna share my iPad instead of my laptop. So it should be good.
Okay, so okay. So I think we should start with Tulsi and then later Soham. So Akshay, how much time it gonna take so that we inform Soham to join later?
Like 20 minutes?
Okay,
20?
so Soham, it's up to you whether you want to stay in the meet. I think you should stay for 20 minutes and then we will discuss with you.
Yeah, sure, sir.
Okay, please Akshay, you may go ahead.
So, could you please share your screen, Tulsi?
Yes, I'm doing it right now.
Yeah, and could you kindly open the different architectures first? Like, it will be better to understand.
Okay, different architecture. Can you see my screen?
Yes.
Perfect. I'm gonna here. Yes.
Yeah. Um. So yeah. This so have you gone through
Yeah.
the task? Like the task written here?
What did you say? Can you repeat, please?
Yeah, yeah. On in the first notebook, like the task are written. Have you gone through the task written there?
Yes.
Yeah, this task. So, okay. So, yeah. So you might not be aware about what exactly average multi-unit implementation is, but fine. One can also try unity of separation by other methods and different quantum encoding. So different quantum encodings here you can try is binary encoding that we have discussed yesterday. And this
Yeah.
method, what you implemented, right? Um, this method uses these 3 points. What is said. So first is incorporate measurement as activation function. How like we are measuring in between, right? The
Yeah.
yesterday the architecture which we discussed, like we are measuring the top qubit and the bottom qubit. So that measurement is used as an activation function as in this activation function what it should do, it should like you can say uh, So not map. It should assume that non-linearity exactly. So MNIST dataset, what you implemented it for, is a degree 3 dataset, right? And what
Yeah.
you're implementing unitary, it's a unitary constraint linear regression. So it will not be able to exactly map to what your target states you want. So there should be some kind of non-linearity imposed to assume that non-linear function of mapping. So that is why, like measurement is incorporated here in the top and the bottom qubits. So, and second is dimensional reduction. So how exactly dimensionality reduction is taking place here? We are measuring the top and the bottom qubits, right? So input features are of the size 64,1. We are measuring the top and the bottom, so the remaining only will be 16, as we have
Yeah.
gone through, right? Yesterday. So
Yeah.
that 16 features is nothing but dimensionality reduction here. And but you will be having access to all the major features as well. So we'll be going through the code below. And third is the like we have used ML pipeline here. So as in we are we are getting the output sheet. So now we'll directly move on to the code. So the case
Okay.
one, what we have taken first is parameterizable unitaries, and this is the, like you can say, pre-processing, as in quantum encoding of the classical dataset or whatever is done here in the first load, right? We've gone through like yesterday as well. For, yeah, quantum amplitude encoding, you can say, for this case. Yeah, just give me a second.
Yes.
Daisy. Uh, yeah, yeah. Uh, yeah. Oh, yeah. Just give me a second.
Yes, take your time.
Yeah. So yeah. So this implementation, what we discussed, right? This is first for quantum amplitude encoding. Yeah. So yeah, so this what we're doing is basically converting this MNIST data set, whatever images we have, into digital like format, into matrix kind of setting. That load function what is done here, right? That is basically doing that. And it's done for the images setting, it's done for the label setting into NumPy format. And then this directory defined for MNIST images, MNIST labels. So could you go below?
Yes.
So this is nothing but to define this function basically does what it does is separates. So what unitary we're trying to imply, right? Impose on this data set, as in transform the dataset using unitary. So for that, what we have done is segregated the data first as per the class label. So for first the start, we have taken for image comma label in the zip image labels. So if label is equal to digits, like we have appended that. As in sequences we have formed from 0 to our end 9 digits. So hope this code is clear. So for so this is done. So if you're like there, so this code will be like exactly same for your part as well. As in we have discussed in the first day itself, in the first discussion itself, but like
Yeah.
let's go over it again. Yeah. So yeah. um
This is all same,
okay,
right?
then yeah, so this, okay, so before
We
to this,
co Yeah,
yeah,
we covered
yeah,
it yesterday.
okay, so we were trying to cover it now as well, but fine, cool. Our song we'll go through later. Okay, fine. uh, yeah, so same whatever you done, right? Above same is done for the test data set here.
Yeah.
So this is written for the test datasets. Yeah. So this is written, right? Download the MNIST dataset from here and you can change the directories. You have already changed. And no, you have not changed. So this is my directory itself. Like, okay, fine.
Yeah.
Could you please? Yeah, go ahead.
Yeah.
Yeah. Yeah. So this is test dataset. It's amplitude encoded here, as you can see for I in the range length, right? This divided by np.linearity.norm.
Yeah.
What's done? Yeah. That section basically. It's normalizing, and then, that is nothing but our amplitude encoding. It's converted into array format, then tensor format. Then, okay, could you please move ahead?
Yes.
Yeah. So these are the results after like plotting. We have just printed that, and that is the reshape result. So this is 28, 28. Then we reshaped it to this specifically is 8, 8. This images. So it's just having 64 pixels. It's easy for, you can see the number of unitaries. So what you can try, second thing is you can try increasing the feature space to what it was previously. For quantum, it should be like 2 raised to n space, right? So that is why
Yeah.
like you can try increasing to that scale. So now it's 64, 8, 8. So you can try increasing 16, 16, like that, 32, 32. Up till 32, 32 you can go, and then subsequent like unitaries you have to train. So our if you understand our architecture 32, 32. So if you like understand our architecture yesterday what we discussed, there it will
Yeah.
be like 2 more unitaries will be there. right? Because at the end, like whatever target states you have, that should be just 4 qubits. That should be having just 4 qubits, right?
Mm-hmm.
So that propagation. So for this case, for 32,32 case, starting will be 10 qubits. Then you have to measure top and the bottom. Remaining will be just 8 qubits. Then you have to measure again top and bottom. Applying a unitary, there are just 6 qubits. Then top and bottom 4 qubits. So 3 parametrable unitary you have to apply after the main unitary. So hope that point is clear. Yeah.
Yes.
Okay. Yeah. So it will be fairly straightforward as you look into the code further. Yeah. Yeah. So this is our method one. So exactly the same code remains true for all the methods, the subsequent method. The changes we'll be discussing, so you'll have to you'll have clear-cut understanding of what changes you can do in this code itself to implement the suggested methods or on other methods as well, given in the next like you can say in the committed section. At the end also there are some tasks mentioned. So what basically these are all the libraries that are imported. Then if you're having GPUs, then this line is useful to you. So then this custom reduce all-in-one plateau, basically what it does is you are having your learning rate defined in your reduce all-in-one plateau to be a fixed value. If you want to go below that, this code is basically defined for that. You can remove this code, that is also fine. You can directly reduce all-in-one plateau. But what happens is for unitaries, like whenever you train your unitaries for larger matrix sizes, right, the values goes to a subscale of 10 raised to minus 10, 10 raised to minus 11, that scale. So that is why, like for training to that scale, the learning rate should be very low. As in, if your learning rate is let's say 1 e to the minus 10 or whatever defined by reduce all-in-one plateau, that's stage. If you stop at, you'll reach to suboptimum level. You'll not go below that. So that is why like this code is written. You can try ignoring this. Fine. Please move ahead. Yeah. So now this is our main like section here. So what we have done basically is define create target state. So what is here is basically done is like for 16 as we discussed yesterday as well, like for 16 what you can do is like map means whatever stage like whatever states you want at the 16 qubits, right? Let's say you want 0000 state, whatever we discussed yesterday, right? The number qubits that doesn't belong to any class. 0001 state belongs to class 1, that was defined by us, right? Yeah.
Yes.
These ranges are defined here. So if you look at this 0 to 5,000, right, and the first, as in the first like element of that, 5,000 to 10,000, the third element of that, 10,000, 15,000, the fifth element of that, like that, these elements are defined. So what this element basically in the ranges means like it the first element of okay no. So this are nothing but the ranges that are formed for the data sets of whatever you have. So this 0 to 5,000 nothing but the target like classes, as in we are having our classes, right? 10 classes. So we are having 5,000 elements in the first classes, and it is indexed. I mean, you can say it moves by 1 month. So these are nothing but the ranges. Then for R in the ranges, what we are doing is basically from R0 to R1, comma R2. So we have at specific position defined right value to be 1, right? And this are nothing but creation of target. So this is like create function target to be defined. Alternative for this will be already shared. Right? The alternative for this is the code which we shared
Your
before.
voice is really low.
Okay. The alternative for this is so the create target state functions is clear, right?
Yeah,
Or like yeah.
I
So
could hear.
alternate yeah. So what this one basically is, at what position of 1 you want, means for let's say for class 1, where exactly one you want in that probability amplitude 1 and remaining probability amplitude 0 you want in that 16 cross 1 vector for that particular data set. That is what this implies. The second alternative to this is you can directly define your, so because like this is not let's say you can form a states, those are not equally spaced, they can be having one spacing, but you can write it separately, right? So this is useful when it is less than 4 qubits, and in this kind of setup what you define here, define create charges, this is useful for when we're having less than 4 qubits. But since you're having 4 qubits, instead of doing this, what you can do is directly define target state zeros, like target states combined, initiate it to some torch instance zeros of 50,000 comma 16, and then define one state at what index position you want. So let's say you'll define target states combined, and you'll index in that to let's say 0 to comma 5,000, 0 to 5,000 comma the index position what you want at that index, let's say first index position. So 0 is start from 0, right? First index position you define to be 1, and remaining all it will be 0, like that what you can do. So this code has been shared with you in the remaining like amplitude encoding. If you go into that
Okay.
also has the code. So fine. If this code is understood, that code is also like same. Like we have discussed that code that as well. So what this class unitary layer basically does is, right? So what we are going to do now, like we have our target state defined, right? We have to parameterize our unitaries. So how many unitaries we have for this case specifically? Two unitaries we have. As in the starting unitaries, the first unitary what we discussed. So if you'll open the doc which was shared, like it's open there, right?
No, but I have it in front of me on my laptop. Give me one second.
Okay, fine. So whatever doc was shared with you yesterday, like it has three parameter units written there. So for this case, it will be two parameterable units. This implies like this has both the unitaries defined here, and then at the output, the state what you want, that will be the forming the state and then the target state. So that will be there in the loss function. So we'll start with the code. So this are nothing but the initialization parameters. So this in features and out features are nothing but the arguments that you pass in a unitary layer at the start. And then this self weight, what it basically does is it defines the based on your features, it defines the weight matrices adding weight. So we have not added a unitary constraint still now. Like this nn dot initial orthogonal adds a unitary constraint for
Sorry.
initialization. Yeah. So
Okay.
it it adds a unitary constraints for initialization. What this orthogonal basically does is, like it will have your rows and columns made orthogonal, but what we want are orthonormality. Just for initialization of weights, it does this. Okay, fine. But
Okay.
what we want is the subsequent unitaries should also be unitary, right? Subsequent as in matrices after back propagation also should be unitary. So specifically for that, defined make unitary function is defined here. So in the defined make unitary function, there are like two approaches we can follow. Like first is our SVD approach. Sometimes what happens, like the optimization is not reached using SVD approach as in least square methods, because you're integrating a least square method here with your ML approach, right? So it so happens like sometimes the optimization is not yet for certain back propagations, as in certain matrices of the back propagated for certain epochs. So that is why, like instead of using first, you can use the second approach, QR decomposition approach directly for finding that unitary matrix parameters will unitary. So hope this is clear. So this code is already clear, right? What this Q is basically your unitary matrix. That R is basically your upper triangular matrix, and we are returning just q at the return. So this diagonal what we are returning, right? This is a more optimized form of the unitary, as in it will give your error norm to be lesser than even if you're using float 32, right? The error norm will be lesser, as in u into u dagger of I should be like nearly equal to I with a precision of 10 raised to 7 10 raised to 8 minus 8. So that is why like this is input. Like you can try removing this, just q is also fine for your case. Fine. Then in the forward function, what you're doing basically multiplying our unitary. So this unitary what you have, right? Those are multiplied with the weight vectors what you are passing as the input. So unitary weights, what self dot weight we are initializing here, we are making that unitary here, and then we are returning the nn dot functional linear of x comma unitary weight. So this value x comma unitary weight, what you can do is basically directly like multiply this, as in instead of returning this, what you can do is multiply your x directly with the unitary weight. Okay, but yeah, that is also fine alternative. So this is a recorded section. Fine, you want to write, you can find. Okay. So now coming to our second class. So this is our quantum model, or this is where your architecture is basically defined. So
Mm.
up till now, so up till now, what we have done basically, you define a unitary linear. So what will basically it will do is, it will have a forward method in which you're initializing your weight, unitary weights, and then multiplying that with a linear like x. That's it. This function. That's it. It's doing, and then you're passing that to this, as in self unitary one. So you are both two parametrical unitaries, right? Self dot unitary one, self dot unitary two. So those are initiated with the arguments of input and output features, which are initialized here in features out features. Hi Tulsi. So your screen is not visible. Yeah. So
Oh,
this.
it's visible now. I'm so sorry. I was just checking.
Yeah.
Okay.
Yeah. So this unitary layer 64,64 and this unitary layer 16,16, basically what it does is it passes the values which you want. So as you're passing your x value to be 64 cross 1, so that value of unitary will be 64 cross 64. So that is initialized here. Second initialization is done 16,16. Now after measuring, right? So top and bottom measure qubits will measure. So it will be 16 cross 16. Fine.
Yes.
These are both initialized. Now in the forward architecture is what our main architecture will be implemented here. So in the forward architecture, like what you're basically doing is passing that self dot unitary 1 to your x. So
Mm.
so this so at the forward method of your class unitary, this will be unitary layer will be nothing but a parent class here, and this will be your child class quantum model, and you're passing your unitary layer directly here, right? So self dot unitary 1 of x, what it will basically do is will multiply this, right? Unitary into x it will multiply, right? So that point is
Mm.
clear. Yeah. So
Yes.
now, yeah, so in the second point of this, x is equal to x dot view. So what this basically does is, we discussed this yesterday, right? What this basically will do is will convert your reshape your input vector after multiplying with the unitary. It will reshape it to 2 comma 16 comma 2, right? Then this line is what you can comment out the second after this, x is equal to x dot permit. So that was tried, but you can comment now it now like for now, because that is not required in the subsequent method. So this line after this, x is equal to x dot permutate 0 comma 2 is basically indexing, as in it's indexing your 16 back to the second position from the so 0 as in batch is kept at that first position, then 2 will basically 16 will be coming at this point, then the first position 2 will be indexed at this point. So basically this you can comment it out. This main thing is this, x equal to x dot view minus 1 comma 16. So this is your main thing. What it basically does is it flattens to your batch size. So it's written in the comment as well, but you don't follow this comment blindly, because the same code is taken in the below as well, and then I have not commented out this section, as in it's not exclusively commented back. So flatten to batch size star 4 comma 16. So this is basically doing that. What it basically doing now, we are increasing the size of the data. So hope that point is clear, as in now our size will be whatever 2 qubits you measure, right? That 2 qubits
Yeah.
will be so what our size will be, what reshaping will be doing, as in 2 comma 2 comma batch size, right? So it will be batch size into 4. So priorly it was just batch size and your data set. Now it is batch
Mm.
size into 4. So basically dimensionality is reduced, but data is augmented, as in data size is increased. So that augmentation is here. And then like you're normalizing all that, because using in quantum computer, like yeah, so my voice is heard back, I think. Yeah. Okay. This x is equal to f dot normalize, what is basically it is, it normalizes that, as in quantum computer, when you measure one state, or automatically by Copenhagen interpretation, the second state as in of the same Hilbert space will be normalized. So that is like specifically like imposed here, normalized in the dimension one. So fine. And then the dimension one is nothing but 16. So this x is equal to, now we are passing the second unitary. So hope this point is clear. This
Mm.
is basically data augmentation in the first layer, right? Okay.
Okay.
Yeah. Fine. There are like second approaches here, like other approaches. So instead of like 2 3 approaches are there. So if you so I'll explain to you this code, then we'll second block and third block whatever is written, right, for different architecture are like simple straightforward based on this only there. So you can go through on your own. Like we'll just touch on the changing points. So this x is equal to torch mean of x. So what is like okay, so could you go back to the previous code?
Yes.
Yeah. So this is nothing but, again you're changing it to your batches. So okay, so this implementation, basically what you can do is data accommodation also can be tried here. So what we are basically done here is we have taken the mean, as in we have again reshaped it to for batches comma 4 comma 64 16, and then using for the dimension one it is mean. So whatever output size will be batch size comma 16. So this return mean is done, right? So that is done on the next slide as well. So could you go to the next slide? Yeah. So what we are basically doing is, instead of data augmentation here, we are just taking the mean of that quantum state vector and returning that mean as in a single state vector. So what basically mean implies here is, whatever state of measurement you have, 0 comma 0 or 0 comma 1 or 1 comma 0 or 1 1, there are 4 possibilities. Out of that you're returning the mean. Out of the all possibilities you're returning them. This is not possible actually in quantum computing, but for training, like this is our first method, we are taking the mean of that. So second approach will be data accommodation, and third approach will be other way of not take, instead of taking mean, like what we can do that. So instead of taking mean, we can take the highest probable state, that only single state, and then discard the remaining state. That is the third approach. Like that we are following that kind of setting, right? So hope this point is clear. Now this is your define quantum loss. So what this basically doing is, so again you're normalizing the state. So this, so you can try like incorporating different loss functions here as well. So we have tried just your MSC, just your absolute mean square error. So that you can try, so, as in so what basically you're passing in the arguments is what your output state you have from your previous class. So this is your normalized state, and then target state. So target states are defined at the start, right? That creates target states function, those are defined here. And then yeah, so this is nothing but your absolute mean square error. But yeah, and then training loop. So define training model. This basically is your training loop. So Adam W optimizer is used. So this is like best for now. So don't you don't need to change this. And this custom reduce already on plateau, like you can try instead of this reduce already on plateau as well. The arguments will remain the same. Yeah, and that change can be done, but try to keep it as it is. As in some lag will be there in running the code. We'll run the code slowly using custom reduce already on plateau function, but yeah, kindly give it as it is. Then this is your training loop. That's it. So what basically training loop? You're like setting your whatever weight values are there to be 0 for the next epoch. As in when you will pass the first epoch, then the second epoch you are setting it to 0. The grad values in the derivative value what you are getting after back propagation, those values will be set to 0. Then outputs will be nothing but model of input. So whatever forward output will be there, it will be written here. So this vector is written here, and then the loss function between the outputs what you are getting from your model and the targets are minimized. Loss backward for function. So this is nothing but that. And then this essentially again you can say clips, or this again is not needed, but this essentially clips that norm in the range of 0, and for orthogonalization itself is done, but you can remove that step as well, not needed. And now optimizer step, and then scheduler step loss. So that is incorporated here. As in if the loss function doesn't decrease, it increases, and the learning rate is basically reduced here. Yeah, that's it. And then if it is the epochs are like from 0 to 4, then this print statement will be executed. Fine. Okay. Then this is where your input data and output data are placed. The model is given assigned you can say this instance variable, and then yeah, the train model function is initiated here. That's it. Okay, and then this is your evaluation on the test data. So how is your train model performing on your test data? That is nothing but this. And yeah, so yeah, could you go on the next slide?
Yes.
Yeah, so this is nothing but the post processing of your like predicted labels. So whatever, yeah. So this predicted state train vectors what will be giving at the output, quantum predict input vectors what will be getting at the output from here is basically the 4 as in 16 cross 1 vectors, right? And those 16 cross 1 vectors will be your target vectors, or nearly be equal to your target vectors. Now there are 2-3 ways of post processing here. What you can do is basically whichever probability amplitude is maximum, you can try returning that as in the index of that, and if it is near to what you assign that label, right? As in let's say this is in sequence, right? This is input vector. So for sequence of 0 to 5000, if it is for first index, if it is returning 1, if it is returning 1, so let's consider 0 to 5000, and for first index, as in first position of this predicted chain vector is returning 1 or nearly equal to 1 or having the maximum value, then your class will be class 0. If not, whatever maximum value is written, that will be your class. So that is nothing but what we said in words is nothing but done here, right? So this input numpy is done, and then actual labels are nothing but this. This is your actual label, because you are separated your image and labels and you are segregated from start 0 to class 9, right? Then predicted labels will be nothing but np.argument max, as in what is your maximum like position in the predicted 10 vectors that will be returning. So hope that point is clear. As in let's say your maximum probability amplitude occurs at 2, occurs at 3, occurs at 4, like that. So this np.argument max will be returning that position at what index position of that vector it it returns that. Hope that point is clear. Now it is returning the position, right? But we don't want the position, we want the class assigned to that position. So here it is done. So if the target state, so whatever target states will be having one value, right? That one value, so if m is equal to 1, so as in your class 0 here, So
Mm.
assign class 0. If m is equal to n equal to 3, as in if at third position the argument as in probability amplitude is maximum, then append 1 like that. So if it is maximum at the 5, so this is, I think, some mistake is there. Append 1 is not yeah, yeah. So this should be 2. Yeah. So yeah. So that might be one of the reasons for decline in the accuracy. Once check the code. So yeah, as in. It was done like in a fast way, so we forget. So rewritten, I think the accuracy is 66 or 67. So I think the accuracy will be increased to, let's say, 70 to 75, or maybe it will be 80 or 85. But you have to like run and see. So basically, this is our function that is initiated, and then you're passing your function predicted labels from here, which are having the index values to this to convert into class variables. And then if they are matching your actual variables, those will be returning the matching counts. So these are nothing but the matching counts, and they will be getting the accuracy. Similar function is done for the test vectors. That's it. And in text vectors as well, then this will be an error because the same code is taken there, I think. Please go there. The same code, yeah, because the same function is passed there itself for the predicted train test labels. In the next slide, if you go into, yeah, so same function is passed, right? Index label conversion, predicted labels. Yeah, so this will also change. I think the accuracy will be increased now. Yeah, I'll try to make changes, and will yeah. So this is nothing but the like epochs printed by epochs printed per yeah. So this accuracy I'm talking about, this train and test accuracy, what you're getting, right? Yeah, should be increased to 70 to 75 like that, or at least 80. Yeah. Yeah, so fine. This method, if one is clear, the subsequent methods all are same. There is nothing change in the code. There are 4 factors that will look into what their changes are there. So what changes are basically average of the quantum state. As in the previous, if you'll see what we have done, average at the end we have done, right? That is not the actual quantum phenomena that is happening, but we have taken as the average. As in global sum of all the possible measurements were taken, and that will be a single state vector we are returning instead of like taking the maximum possible state, as in maximum probability amplitude, what will statistically what will be occurring, taking that state we are taking the mean. Now here what we'll be doing, in between unitaries, like there are 2 unitaries, right? After the first measurement also will take mean, but in the prior we are not taken mean on the first side, we are taken mean at the end. So in the first also will take mean, in yeah, in the second second will keep it as it is. In the first, in between will take the mean. That's it. Means before applying a second unitary will take the mean.
Sorry.
That's the only thing, yeah, done here. So what changes you can do here, like if you understand the if you understood the code clearly, what changes you can do here, instead of taking mean, what you can do is try data augmentation and keep the section as it is, but your loss function will be changed in that case. So how your loss function will be changed, as in you have to initiate it in the loop. You have to initiate your loss function. So what loss function is defined here, right?
Yeah. Wait,
Yeah,
where
so
is
this all
this?
code is same. Yeah.
Wait.
Yeah, please go on the next slide. This code is
Yeah.
remaining same, like everything is same, everything is same. So this, as in, if you look into in your forward method, so what we are talking about basically is this, this mean section what was there in the last right line. Instead of that, we have taken mean onto the fourth line. If you look into x is equal to tot dot mean x comma dimension 2 comma 3. This is nothing but the only change done here. So there are like 2 4 architecture changes you can try. What 2 4 architecture changes? Instead of taking a mean here, keep the data as it is, reshape it to 4 comma like 16 the size. What was done in the previous case, right? Batch size into 4 comma 16. So keep the data as it is, and for every like vector, what you can do is pass it on to the like quantum loss. So instead of taking a mean there, quantum loss, so you can write a sentence here for I in your output vector, and then in that loop, as in for I in the range, your I in the range, your total data set as in 50,000 into 4, that is 2 lakh. For I in the range 2,000 2 lakh, output this torch dot absolute of output, right? Instead of passing this will be in the loop. You'll initiate your loss function equal to 0, then this will be in the loop, as in torch dot absolute of output of that corresponding I, and what is the corresponding target for that, because you're training, you will be having a target value, right? So it will be in sequences only. So so again for target, like if it is first, let's say if it is first 20,000, if it is first 20,000, it will be assigned a class 0, right? So for the first 20,000, your target vector will be your class 0. So hope this point is clear, like what I'm saying. You will have to make changes in the quantum loss function for the data accommodation. I'm saying data accommodation.
Mm-hmm.
Is it clear? Is it not clear? So these are not changed. This latent to batch size 4 na, don't follow the. So this is not done here because you're taking mean, right? Yeah, this is not. So this the shape will be batch size comma 16. Yeah. Okay. Because the same code is taken here and like only changes are made. We have not like done the remaining changes. Cool. So hope this point is clear. No, this will not change here. You have to implement that method 3 in that. So this is clear. This is clear. The implementation is clear. Like throat is okay. But in
Okay.
the method, yeah, subsequent fourth method or fifth method, when you will not reduce your like size, you will take all the data sets as in all whatever measurements you have. Zero,
Mm,
zero. If the first qubit, second qubit, last qubit is 0, 0, then the state vector. 0, 1, then the state vector. 0, 1, 0, then the state vector, and 1, then the state. That four state vectors, what you have, that will be multiplying with the batch size. You will be reshaping your you can say this input data and data accommodation and the increase in the size, whatever it plays. So that's what I was explaining. Like 2 lakh, comma 16 will be a data size output size, and that for that corresponding target vectors also you have to change. As in instead of 50,000 comma 16, you have to increase that to as 2 lakh comma 16 as well. And then keeping the target vector same, and then you have to initiate this. So this can also be kept same. Then in that case, if you're increasing your target vector also to be 2 lakh comma 16, right? Then this can be kept same. So alternative of using for loop is increase your target size to 2 lakh comma 16 and implement that method, that of data computation, and then see the result. So what that will imply basically is all your four vectors, whatever those are data augmented for of that particular class, will have the same target vector. And after that, whatever data will be getting, right, that will be of the output format 2 lakh comma 16 after passing it to the circuit what we discussed. So that 2 lakh comma 16, what you can do is you can apply voting max algorithm or any other algorithms like having the voting accuracy. So we have four samples, right, for the same like input. We have four output measurements for the same input. So you can apply statistical like theory of max voting or other alternative theories to infer using that. That's four instead of one. So hope that point is clear. Is it clear, Tulsi?
yeah, I will have questions. Right now, it's clear to me, but I'll have
Yeah, sure,
questions
sure,
later.
sure, sure. Cool. Yeah. So please move ahead.
Okay.
So same code. Everything is same. We have discussed this.
Okay.
Yeah.
Oh, sorry.
Uh, Yeah, so like for both the cases, whatever implemented, there should be at least a 6-7% increase in the accuracy because one class is totally misidentified to a class that is one. So yeah, upper class. So yeah, fine. And the next implementation of this, if we move on to method 3, yeah, we are over time now. It already 36 minutes. So like please bear with us. Like yeah. Um, so this is the method 3 and in this like alternative way of indexing is implemented in method 3. So what you can do is try implementing this indexing method like for your fourth like data accommodation to fine hai. लेकिन mean लिया है पहले, like we have taken mean on the upper two sides. So this indexing format was not like specifically required. We have directly initiated it to like reshaped it to 2 comma 2 comma 16. We discussed that point yesterday as well, and then we have taken the mean. So instead of that, like here it's properly initiated. If you go into the next like section, so this call code remains the same. Yeah, so this all code remains the same, everything exactly the same here. So indexing is implemented here. If you look into this block 1, block 2, block 3, the commented section also giving you clear cut picture. So which component is which, as in if measurement is 0 and measurement is 1, so this is your indexing part, as in whatever vector you have, all the samples. So for that, the top 32 elements with the spacing of 2, if you take that x as a vector, that will be forming a block 1, and above that will be block 0 if the measurement is 0, 0, like that. So hope this point is clear. In the second section of 32,64, you have taken indexing to be 2, as in the spacing to be 2. Then like you will be having this setup, as in measurement for first qubit will be 1, then the j will be your like this feature space, and this 0 will be your last qubit measurement.
You got cut off.
Huh?
You got cut off in middle.
Okay. So from where, like,
Yes.
could you please? Yeah. So you understood this point? Block 1, block 2, block 3. This.
Yes, I understood that point.
Cool then, cool. So this is nothing but whatever torch norm, like what is the norm of that particular block we are taken. So you can remove this totally because we are anyways normalizing that. So that is done. So yeah. So anyways we are taking the norm of that, and then yeah. So here another method is implemented. So why we are taking the norm per se for of this particular blocks is basically because we are assigning after measurement we are just taking a single state, and what state will be, that state will be having a maximum probability amplitude of particular blocks. Let's say block 0 has the maximum norm out of all the remaining blocks for a particular sample. Then that you will take as the block. Hope that's point clear. Means as in
Mm.
what, yeah, block 0 will be having what, then 0 0, right? Both qubits will be having 0 measurement. Then that particular block will be having maximum probability of occurring if that assigned norm is maximum for that case.
Okay.
Yeah. So why this norm we are taking basically is because like you are so x is normalized first, right? X is normalized, that point you can agree, right? But now you're indexed, right? You're indexed and you're not normalized. So what that norm will be, that norm will be nothing but your the norm that is remaining, right?
Yeah.
So yeah, are you getting the point? As in 0 and 1. So what is the
Yes.
actual state of this point to be occurring? That probability amplitude will be this, and based on that, whichever is maximum, you have taken that as the like maximum probability amplitude, and that is the state that will occur. That is what the basis here is of implementation of this, and the remaining like block is same. So select the 16 with the highest, like this is written here, with the highest mod square, mod b square, mod c square, mod d square, as in whatever norm is maximum, that is nothing but like we are taking, and that measurement, that quantum measurement as a feature selection we're taking, or that quantum measurement as the activation function we're taking. So hope that point is clear. And then select 16 cross 1 vector blocks using advanced indexing. So this is nothing but what the measurement indexing basically does. So you can try implying this, implementing this. You can try reshaping as the second method, but reshaping doesn't work when the state is in between. So that is why like this method is implemented. Fine. And yeah, and the remaining code blocks remain the same. So yeah, and this is the other way of indexing. You can go through this code as well. So yeah, cool.
Okay.
Yeah. Then yeah, so remaining code remains the same. After this, like yeah, so in this also the accuracy will change, whatever the accuracy is. So it's 1 1 there, right?
Let me see. Yeah.
Yeah. So same. Like after this, like there are two tasks that you have to implement. Like I don't know if the data augmentation task is written specifically, but that also you have to implement. Like you can add it now.
Okay. Here,
Okay.
right?
So the what was the fourth method of implementation?
I'm sorry. Fourth method of implementation. Yeah.
Yeah, so this, yeah, so instead of selecting the maximum possible state, as we very well know, statistically, even if the state of occurrence is having maximum probability, the state that will be occurring will be conditioned on that. State can be having any occurrence, as in based on that probability. So if you're getting the point, let's say if you are having 1 by root 2, 0 plus 1 as your state. So what is the probability of occurring 0 at the output is 1 by half, like half. That's it. So half times exactly you will be having 0, half time exactly you will be having 1. But actually when you carry out the measurement, it will be random, right? It will be conditioned on the probability amplitudes, but it will be random. So similarly, even if it is let's say 1 by 3 and remaining is 2 by 3, the probabilities I'm saying 1 by 3 of occurring 0 and 2 by 3 of occurring 1. So even if it's conditioned on the probability, the state that is occurring after measurement is exactly random. So that is what is initiated here, random state after measurement. So a random state of the 16 state vectors we are taking, of the 4 possible 16 vectors, only one state is taken, as in randomly we are taking either output to be 0 or output to be like output is 0 0 of both the measurements, output to be 0 1 of the both the measurements, output to be 1 0 of the both the measurements, or out of 4 we are selecting one randomly. So first the criteria was having the maximum probability amplitudes, as in the norm associated with that. Second criteria is this. So but this is giving a random accuracy. So if you look into accuracy of this as well, the above as well is very less, because
Mm-hmm.
there is information loss after measurement. So that is why it's showcased here as well. If you'll repeat the fourth experiment and you'll like append all the data what will be having, right, from the accuracies, then it will match the method fifth accuracy what you'll be getting, method fifth, as in data accommodation, that is not implemented here. It will match that because all the state will be recreated exactly and then it will match it. So method 5 is, I think it's written here. So you can go through what is written here. Method 5 of, so on the next,
Yeah.
so this is random. Yeah. So if you run it again, right? 53, 56, whatever values you'll be having, that will be random. So instead of taking average as method 1 after data computation, one can apply voting. Yeah. So this is nothing but method 5 is already written here. You can try implementing this. And if you have any queries in this, like, and what you can try researching is other like ways of like, so this is just ways that we came up with after going into details of the algorithm. Are there other ways, like other implementations you can try to improve the accuracy of the algorithm? That is what you research on your own. So yeah, so hope the high level overview is clear for this, and then you can try this as well. All the our methods can be implemented with non-parametrical unitary. So this is again what you can try to implement. So what we have taken here is parametrical unitary based on the back propagation, right? So instead of that, what you can do is apply an unitary by SVD approach or unitary by ML approach for exactly mapping to target states, and then similarly like subsequent, as in, yeah, yeah, for this case it will be difficult for you, but you can try implementing that as well. So because you have to implement that indexing in between, you have to implement, and that unitary you have to reduce and then multiply with the next unitary, what you will get by SVD, and that both the unitaries will be having a target states of what we discussed. So yeah, that task you have to try. If it's possible, you can try, or you can keep the last task as well. But this method 5 to implement and try researching other ways. And whatever discussions we have yesterday, right, you can try those as well. So hope this is clear. Now we'll move on. So this you can try voting max, stacking, boosting, whatever vectors you'll get right at the output.
Yeah.
So the after data computation, this method you can try and see whether the accuracy increases above 90 to 93%. And other encodings you can try for this, right? Hope this point is clear. Could you please move on with the initial quantum algorithm? So if you understood this, right, that will be fairly simple to understand the implementation. Yeah, so go through the comments written here, like it's exactly carefully thought and crafted out for this, particularly for you and for this project. So these are your tasks. Yeah, go through this, and yeah, so this code block exactly remains the same what we discussed. Again, this code block is exactly the same. The pre-processing for every algorithm, like for MNIST dataset, is same for our implementation. Okay. Now from here our actual code starts. Like yesterday, so you if you're having if you'll be having our doc in front of like you know exactly yesterday what we discussed is basically your Kronecker producting your ancilla qubits with your input quantum encoded states, right? So this is done here. So input state vectors are this, and your Kronecker predicting that with your input tensor producted state, which you initialize it to 5000, 1024. For reducing the compute size, we have taken from 50,000 just to 5,000 case. Okay, and this input ancilla 0, what we have taken, right, that is equal to 1, as in which we already discussed yesterday. The input ground state, input qubit state should be having the state as 0000, right? As in for 4 qubit ancilla state, the start qubit will be 000. That's it. That in vector format is nothing but having at the index position 0 to be value 1. So that is Kronecker producted with this, and it's taking amplitude encoding is implemented here. So yesterday I had written a comment in laptop amplitude encoding. So here basically the amplitude encoding is implemented of your input vectors. When that is clear, the target vector. So in the next code block, this target vectors are nothing but like first return. So what those target vectors in your higher space will be. So as in in the target ancilla label state, if you look into NP0s 16,16 is done here, right? So for this case, like okay, so why is 16,16? Okay, there is some I think so there is some error in this code. It should be 50,000 comma 10. Okay, no, so this is 5,000, this is
Yeah.
fine. Yeah, this shouldn't be this should be 50, this should be just 16, right? Just 16 this should be. There is some error here. Yeah, np.0 is 16, it will be not 16 comma 16. Yeah, okay. Now this target ancilla label state 0 to up to 15 we already discussed, right? So how to get this, basically the state is like yeah, so you will be multiplying your ket. So basically this is vectorization form of whatever state you have. So all the states possible 000, 001, 00 0, 0, 1, 0, the ancilla qubit states are nothing but vectorized here. So these are nothing but the vectorized form of the states, and from 0 to 15 all the states are vectorized. That is why the like shape should have been 16. I don't know what the shape, why the shape is taken like that. Anyway, so this target ancilla label states, so there might have been blunder. That blunder would have been like in the subsequent code as well. So from my side. So anyways, kindly correct that. That is fine. The target ancilla label states are nothing but your this. So this is printing format of that. Fine, cool. Could you
Okay.
please go? Yeah, go on ahead. So this point is clear, right? You just vectorize
Yes.
that. Yeah. Now, this, so out of this, only 10 class labels are of your use. So only 10 class labels of your use. So you can assign that as in for what label, as in let's say for input state vectors, indexing to 500, and then the first 500 belongs to class 0. We have separated that to images and labels, right? The first 500 belongs to class 0. So that is why at the start we are assigning at index 0 position. Okay, this is again a mistake from our end. So this shouldn't be 0 here. This should be 1, because you are making the state as 001, right? So this should be target state labels of mapping should be 1, having indexing 1. Then the subsequent it should be 2, like 3, 4, like that.
Wait a second.
And yeah, because it's written there at 001, so it should be having an index of 1. It should be having an index of 2, like that. Yeah. So this state should be having index of 1 corresponding to that. So basically what this is your like number of classes labels, as in you are giving a probability amplitude of 1 at that particular index value. And so remaining code is exactly the same, as in 2500 to 3000, 3500 to 4000, because your data set is limited to 5000. So the remaining code is exactly the same. And so instead of doing this, what you can do is define a function. That will be easier. Don't need to like repeat this code again and again. And in the define function, you can try passing the arguments of what exactly the index positions you can try pass. So that can be changed for every. Yeah. Fine. Then you have gotten your target states normalized. So this your target state. So that is why the accuracy of implementation is not that much. So yeah. So forgive me exactly for the like sending you this code, but like we had multiple things to carry on. So like there are if there are minor errors, like uh, we'll basically we'll tell you from our end. If not possible, you can ask, or you can correct it from your end as well. Fine. So yeah. So this target output quantum states based on algorithms normalized. So basically what your target state will be having, you these are nothing but chronicle producted with your input state, because what output will be having yesterday we did discuss, right? For your first 6 qubits, the output will be whatever your input state is, and for the last 4 qubits the output will be whatever y was initially, that was our 000 XORed with your function of xm. So that function of xm, uh, uh, so this state whatever you get right after that, so this is nothing but chronicle productive. So m comma this value, m comma target states label mapping 9. So this is chronicle productive. This will form your target states, and then this code is already been discussed with you. So this is nothing but amplitude like normalized basically. Yeah. So
Oops.
normalization is done of the target states. And this the upper part of that is chronicle productive. So I missed that point. This point at np.crom. No, not this. This is normalization. Above
Oh,
that, I'm saying.
my
So
bad.
that is why cursor was needed from my end.
Yes.
Yeah. This np.cron. Yeah. And basically the below side is normalization. That is done. Okay, fine. Now this code you already know, unitary by ML approach, right? No, so we
Yeah.
did not need to discuss this, because the same code what we discussed at the start. First point is no, not today. On the first day, which we discussed, right? First discussion that code is implemented here. You have input vectors, you have output vectors, and then you're basically training a unitary under normalization constraints, under the unitary constraint. So here also a better way to write or optimize this code is define a make unitary function instead of the putting in the constraint. So if you go into next block, so this same custom already on practice units, this next block what you have taken, right? Here itself you can define a function of make unitary to make this np.linear, which is not having any bias, of like a make unitary function here itself. So whatever initializations you will be doing, that should be orthogonal. If they're not orthogonal, that is also fine, but define make unitary function should be there, and to pass this linear function in that, so that will exactly your unitary. But what we have done here is basically incorporated that unitary constraints here. So if you look into ortho loss 0, ortho loss 1 in the next side, so u into u dagger and u dagger into u should be nearly equal to 1. So that is implemented here, and then returning all 3 losses and combination of that. So but if you're starting from your unitary itself, so no need to do implement this in your loss function. So that would be better, and that would be betterly optimized. So you have to just minimize your RSME instead of minimizing both the orthonormal loss, two orthonormal losses and one RSME. That changes you can do to improve the code efficiency. Fine. On the next slide, if you go into, yeah, this is nothing but the same code. No. So sorry. This is different
It's
code, right? Please
different.
go. Yeah, please go on the backside. Yeah. Okay. Before this. Okay. So it's the same code. Like okay, go on the next slide. It's 18. Just give me a sec. This point is fine. Go on to the next slide. Okay. Okay, up till this is clear, fine, and we are implemented some kind of regulation. At that point is okay, and we have not taken that. Like, okay, fine. Okay, so this. So we were trying different ways to optimize, and this is nothing but one of the ways to optimize. So whatever weights we are initializing, you can initialize that as per the Kramer's initialization, or you can initialize that as to have your uniform initialization. So there are like various ways. So like you can try if the initialization is like you can say suboptimum, then your starting epoch loss is lesser. So you start at lesser epoch. So whatever subsequent epochs, number of epochs you required for getting that optimum is less. So that is tried here. It is not necessary here because you don't have that kind of higher losses to minimize here. They are
Mm.
having lower losses only, but still if the code is optimized using that. No, it's the same. So this is your input vectors, x input vectors. This is your target vectors, and the same thing is done here. Okay, fine. And the training group is done. So hope that point is clear. So what you can do to optimize basically this code is, instead of incorporating ortholos 1, ortholos 2, what your different architecture code was there, right? In that make unitary function was there. That's the same make unitary function you can try incorporating here and remove, or you can keep this loss function as is and print it, and then you can see for every epoch the unitary constraint is satisfied automatically if you like implement that make unitary, right? Okay, then this is the training loop, as in those are nothing but the epochs that are printed. Could you go on to the next slide?
Okay.
Yeah. So that's it. Then the output vectors what you'll be getting are nothing but multiplication of your unitary what you got, and then this. And the main implementation of this comes at later stage. Like if you go into next, so this is nothing but matrix vector multiplication that is done, and the output state train vectors you're getting. Could you go fastly go into the next slide?
Yeah.
Yeah. So this yeah. So now if you go into what you're tied here is basically you already know the probability amplitude of your target state is what we have like in your like loop, means whatever target states you have, the target states combined you have. Okay, so okay, this function is basically not needed for this case at least. So 20 and 21 you can try removing, not needed in this case particularly, because for our case of interest only last 4 qubits are there, right? For our case, but this is needed where exactly in your like implementations of amplitude encoding, just the amplitude encoding starting algorithm which you discussed on your first day. This is not needed here. Okay, then unitary by SVD approach. So this is the second approach of that itself, finding a unitary by SVD. You can try QR as well. So same code is there, like input output features already do. Go to the last block, like after this code has been discussed with you. So yeah.
Okay.
So this like yeah, kindly go through the comments on the next section. Yeah, these comments, and these comments are nothing but, so work out the maths of the linear algebra on paper. So what basically we are doing, right? So that you can work out on paper. So here what you can do is basically reshape, because the 4 ancillary qubits are at the bottom, you can reshape your state of output what you have gotten into 64. The 64 belongs to the top comma 16, or what we discussed yesterday is 16 comma 64. Yeah, so basically what we'll be doing is yeah, so because you are measuring your bottom 4 qubits, right? So you can reshape it into format of 16 comma 64. That you can try incorporating. Or second thing is this, what you implemented here. So what you can do is try writing the states, all the states in bracket notation format. That will be exactly like you can exactly visualize. So if you go into, these are the binary representation that are printed for all the, and the range to 1 to 2 for all the cases. So fine. Yeah, These are all the basis states basically in zero on basis. Those are like implemented. Now, like from here, if you look into, we have just taken the first vector of your output state train vector. Now that vector will be what exactly? A Kronecker product of your first, like Kronecker product of your input image or amplitude encoded input image, Kronecker producted with your target state of class 0. So that should be a state here, ideally. So yeah, so basically when you measure the last 4 qubits, the maximum amplitude should go to your 0001. That is what we discussed yesterday as well. So basically what this code gives is nothing but a binary representation format of that. So this is this for all like what is the state at the output is nothing but printed here. So what is the, so if you can just print the vector format, that vector format is like not Kronecker protected, is multiplied with the basis state. So this basis state is nothing but this. So even if you just print out your output vector of your output state 0, right, in that only we have concatenated the binary digit of the index position of this. So this probability amplitude 6.96866, right, into 10 raised to minus 6, this first state.
Yeah.
Yeah, into this state is nothing but you can write here, you can make changes in the form of printing. So like we have just concatenated that, right? So you can like yeah, in this you can try putting a cat sign, as in cat sign to this binary section, so it will be clearer to visualize. Yeah, not this whole,
Mm,
after this 10 raised to
just the
minus 6.
binaries. Okay.
Yeah, just the binary. That is what is implemented here. Hope this point is clear. So basically, what your output state will be having, right? We are just appended, or you can say concatenated your binary vectors to this state. That's it. Not 10 raised to minus 6 as well. So 10 raised to minus 6 you can
Oh,
yeah.
s-
After this, yeah,
yeah.
starting with this. Yeah, yeah. That's it. The state. Yeah. So for this subsequent, this hope this is clear. Now going to the next implementation. We'll move ahead part. Yeah. Okay. This is the whole state vector. Now what we have to do is, like, we have to reshape this. We have to reshape this to what format? So this okay, so this is exactly done here. So yeah, if you look into what we discussed above, right, so this is done here in the ket notation format, as in the whole the state is written in the ket notation format. Still there is some improvement needed here, so there should be like less than or equal to sign here. So yeah, you can try incorporating that in the code. Go to the next code block first. Yeah, yeah, so yeah.
Okay.
So yeah, this is the main code block. So we are grouping our qubits, whatever you have, right, in the section of first 6 and last 4. That grouping should be done from your case. As in, if you look into print statement of this, go on to the next code block. Yeah,
Yes.
next slide. Yeah. So this is what was like what we are expecting. So basically, if your start state is this 000 after measuring if, like this, so this will be your okay, okay, fine. So again this formatting is wrong. Yeah, is the subsequent code available after this?
Let me check. No.
Yeah, so what you can try to infer from here itself. Yeah, so whatever code we have, you can try to infer, or you can, what you can do is change this number of last qubits, right? The code remains the same. Number of last qubits or number of first qubits should be 6 here. Last qubit should be yeah, 6, and this should be 4. No, so okay, just a sec.
Let me check.
Yeah, no, you have to make changes in the code. The superposition inside stages will not be like this. Okay, fine. So you can try incorporating the changes. So what basically this is, you're taking your first 6 qubits, and then for every first 6 qubits, what is the probability amplitudes of the subsequent stages, or the subsequent 4 qubits that are written here. As in, if you measure your first 6 qubits after measurement,
Mm,
then this is your state. But ideally, what should have been the case, instead of doing this, your 000 should be assigned a probability, as in, if you're getting the point, the last 4 should be in, not outside the bracket, and the first 6 should be inside the bracket, as in all the first 6, because we are measuring the last qubits, 4 qubits for inference, right?
yeah.
Not this qubits, first 6 qubits. So last 4 qubits probability amplitude, what they are, is what you're trying to like infer. So that probability amplitude should be maximum as per that class. So hope that point is clear.
Okay.
Yeah, if it is not clear, like I'll go through this again. Uh, okay, it's already 1 hour up. But this, so what section is implemented here? Basically, if you look into what we want, basically, if let's say your class is 0, your class
Yeah.
is 0, you're taking your first state, right? And your class is 0, which you already know. Then your last 4 ancillary qubits should be 0, 0, 0, 1, right? That should be a state. As
Okay.
in, then you'll factorize the state exactly. When factorize the state exactly such that you'll section it only the last 4 qubits should be there, and the remaining whatever state of the first 6 qubits should be in bracket, like this is written, right? For the first 6 qubits, and the remaining 4 qubits is taken in brackets. It shouldn't be the case. The last 4 qubits and the first 6 qubits, whatever state is, should be in bracket. Corresponding to 000, the state will be one state. Corresponding to 001, the state will be one state. Corresponding to 001, that will be one state. So that last 4 qubit state for class 00001, that should be having a state that is equal to your input state, what you are providing as per the algorithm. If you are okay, if you are clear on that, is it clear?
So they should be having the state that we put in the algorithm.
Yeah, the implementation was correct, but the
Okay.
implementation is not correct. As in, the first 6 qubits should be in bracket, the last 4 qubits should be 000 section.
Okay.
Yeah, bracket means
Oh,
okay.
bracket,
Yeah,
not gate. Okay.
no, not bracket also. Not bracket means like the superposition of that. I'll like share my screen.
Okay.
So just give us 2 3 minutes. Yeah, yeah. I hope the so we have discussed all the things in a code. Like yeah. So this is what we are discussing. So basically, this state, what you will be
Your
having, right?
skin is
Let's
not
say,
sharing.
yeah. Am I sharing my screen, right?
No.
I'm not. Let's say this is class 0. Class 0, you're having your first vector. First output state vector we are taking. It is assigned a class 0, which you already know. Ideally, the output state for this should be 0001, right? Now, whatever the code is written is for this kind of setting, as in you're segregating your first 6 qubits, and then whatever the remaining state is, in that case, what will it be is basically you're measuring your first 6 qubits and then you're segregating your remaining qubits, right? Instead of doing that, what you have to do basically is this should be in bracket, the state should be, and then you have to write the remaining in this format. Plus
Okay.
this first script should be in bracket and this should be a state, like this I was saying.
Oh,
And basically, yeah, if it is class 0, you assign that as a target label of this, right? So
yeah.
this whatever state you will be having here, ideally it should be your input state, what you have passed. That is what the algorithm implies, right? This should be a xm of that particular zeros class, of that particular class, and m is the sample, like which sample it is, and it should have a zero class from the zeros class. So if you're taken your first sample, this first sample state, what your quantum encoded at the input, that should be a state here, ideally.
Hmm.
Yeah. And the second thing is, what you can do is you can check this probability amplitude. What is the probability amplitude of this state to occur? That also you can check. So as in, what you can do is basically, so we have written this, and so this is the state. So you have to measure your first 6 qubits, and then you have to infer your state here, right?
Yeah.
So yeah. So what the state is, but so you can try brain tracking. What may be the alternative that you can come up with? So this is one of the alternative that you can come up with, but this alternative is what it will be computationally exhaustive, like, because you have to again check for every state vector, like whether this is state is present or not. As in, you have to apply some kind of knn algorithm here for checking your nearest neighbor. As in, let's say you are taking ideally your five vectors from each class for let's say knn algorithm training, and you're checking your xm for every for every section. There will be 16 xms that are occurring, 16 xms. In that, only 10 xms you're considering. Every 10 xm you have to compare with this, as in taking a distance parameter, you have to compare with this, and then whichever state is closer, that will be your output. So you have to implement that KNN algorithm. Second thing, you can try brain racking, like how probability amplitude of this can be taken, like maximum probability amplitude of this can be taken, and this will be your output state for this class. So ideally, like this should be your measurement state, but it doesn't happen there. In the code also you can check. So there are like 2-3 ways. Hope this point is clear, Tulsi. You can try thinking about this from your end as well. Hi Tulsi.
I'm sorry, I didn't realize I was on mute. Yes, I will.
Yeah. Okay, fine. Cool. Thanks, Tulsi. So that's all from our end. If you have any queries, you can ping us in Slack.
Yes. Okay. Thank you. Also, I
Okay.
sent you the a request to access the transcript from
Yeah.
yesterday, and I still didn't get access. Can you give me access, please?
Okay, sure. Like I'll be having session with Soham now. Like after one
Yes,
hour. Like
later.
yeah,
It's okay. You
sure,
can do it
sure,
whenever.
sure,
Thank
sure.
you.
Okay, sure.
Have a
Thank you.
good night.
Yeah, you too. So Soham, are you there?
Yes, hello, sir.
Yeah. So sorry for taking like a little bit amount of extra time. I think we are up about 13, 14 minutes. So like we'll begin with your session. Like so 1 hour it will roughly be the session. So we'll move forward directly with the doc file. Automation algorithms, adiabatic, yeah. So yeah, so this so is my screen visible?
Yes, sir.
Okay. So this is what your implementation basically is. So you have, if you have gone through the doc, basically first thing or first step what you to do, and we have been sharing messages as well. So you are about aware about your first step. So what basically you'll do is you will take your image matrix. So this is a nothing but your image matrix.
Yeah.
Then you'll convert that to your Hamiltonian space, as in
Yes.
Hermitian matrix. And we are assuming that it satisfies the von Neumann like condition, in which case, or von Neumann equation in which case, that becomes an observable density matrix, because this is criteria for getting a Hermitian matrix, but it might happen like it doesn't obey the von Neumann condition or von Neumann equation, in which case it will not be an observable. But we are assuming that it obeys the von Neumann equation and it is an observable, and it is an Hamiltonian for our case, for our system. Okay, fine.
Okay.
There are like other ways, more advanced ways you can go into. Okay, this is an OL implementation that is taught, so there will not be a ways for that as in related but directly by this, but you will go into literature and relate the theory with this. And then so
Hmm.
actual way is nothing but this third way. As in, if you take Hamiltonian to be, so if you take your data as an image matrix, you will unitary encode it.
Hmm.
Unitary encode also you can try 5-6 approaches, what we were discussing in the first discussion.
Okay.
After unitary encoding, this equation you can use, as in we already know what your data set we are training on, that is just spatially changing. We are not introducing a temporal connection here. So whatever equation will be using, Schrodinger equation or Schrodinger equation, that will be time tip independent. So basically this equation will come into picture. So you, what you will be getting will be nothing but e raised to minus I h, that's it. And for simplicity case, you have taken t to be 1, that is not time dependent, and h cross to be also 1 from our end. Okay, fine. And this
Okay.
Hamiltonian is nothing but minus I log u. Okay.
Right. Okay.
Yeah. So this implementation, if you do, you will get accurately an Hamiltonian that is an Hermitian that will obey the von Neumann condition. But actually, what happens is when you will implement this,
Hmm.
this is not having a Hermitian constraint. So why it is not having an Hermitian constraint? Because the floating point of your computer, like whatever you introduce, even if you're introducing 64 floating point,
Hmm.
this unitary what will be having, right? That 1 e to the minus 10 loss is propagated into your Hamiltonian matrix, and whatever will be whatever like Hamiltonian will be getting after this, that will not be an Hermitian. You can try implementing and seeing the result. So
Okay.
this, that is why like this step has been implemented as a code format as well in Noel density matrix as well. But
Hmm.
if we try printing the results and we'll try checking whether the Hamiltonian is Hermitian or not, under the condition that u is equal to u dagger, as h is equal to h dagger, as an
Hmm.
h minus h dagger should be near equal to 0. If you try to impose this constraint in the code format, it will be Hermitian to the scale of 1 e to the minus 6, 1 e to the minus 7, but it will not be a Hermitian. We'll look into the like actual ranges, because the range of this implementation will be 1 e to the minus 18, 1 e to the minus 19, in that range. So if
Hmm.
your error is 1 e to the minus 6 and your actual element sizes are 1 e to the minus 16, 17, so naturally this will be whatever Hamiltonian you will be getting will be a random Hamiltonian, will not be satisfying the. So hope that point is clear. So
Yes.
this method you can try implementing for higher precisions.
Okay.
Second thing is, what you can try is reducing the size of the image matrix. That is the first thing you can try. In which case, the unitary what you will be getting, right? That unitary's values will be greater. For maintaining that unitary constants, if you are increasing the size of the matrix, that element values will reach 1 e to the minus 6, 1 e to the minus 7. But if the size is limited, then that values will be greater. And which case the Hamiltonian loss will be lesser by a factor of 10 raised to minus e of 4 or 5. In that case, you can get a Hermitian matrix. But this is an actual implementation. The third, it is also called as Hamiltonian encoding. Right
Okay.
now,
Okay.
yeah. But if you look into using 1, 2, this fourth approach, this 1, 2, and fourth approach, all these approaches will go into, right. These approaches are getting your density matrix, as in just getting your Hermitian constants into the picture.
Okay.
This doesn't by any way imply that your matrix is Hamiltonian. So, but we assume that it obeys and that we have taken that as a Hamiltonian. So, hope that point is clear. So,
Hmm.
yeah. So now the third section. Now, if Hamiltonian belong to particular class, then using the adiabatic theorem. Adiabatic theorem, if you look into, you will have knowledge about from thermodynamics. It is basically what it's adiabatic process. If you look into, it's a fast process that is occurring, and it's a reversible process that is occurring. Fast process, as in adiabatic, is such a process in which there is no heat transfer between your system and your surrounding. That is the thermodynamic implementation of the adiabatic term. But here, if you observe, the process should be slow and reversible. The implementation remains the same, as in it should not exchange the heat between system and surrounding. But here, they have taken the process to be slow and reversible, the opposite of what is adiabatic process basically. So what this theorem basically implies is, so I'll get back to the mathematics part of it. So what this basically implies is, when there is no heat exchange between system and surrounding, what they're basically saying is, whenever, like whatever classes, a particular classes data set you'll have, right? Let's say you have your data set, it is having 10 classes. For
Right.
each class, if you are having, let's say, 5,000 vectors, then that 5,000 vectors you will take, you'll write the Hamiltonians for every image matrix, as in every data in that particular class, and then you'll SVD decompose it, as in, if you'll H this second one was written, right? SVD decompose A, B, C
Right.
transpose, then this eigenvectors what you'll be getting, right?
Hmm.
That eigenvectors will only be, that eigenvectors will remain constant, but this V, that is the eigenvalue matrix, that will change for your data set.
Okay.
Yeah. So what this basically implies is, if you look into pendulum, so I'll explain to you in terms of physical process. Pendulum swinging, that is happening, right? If that is an infinitesimally small amount of duration, it you can think of from T1 to T2 time interval. For infinitesimally small interval, this process that is happening is very slow. So it happens is like in infinite amount of time, you can say, that discretized time from T0 to T1. That, so that will, if that happens, so then this process will be an adiabatic process, and then you can imply this in that case. So hope that physical point relation is clear.
Yeah.
Mathematically, what you will be implying here is basically your eigenvector matrices should remain constant throughout your particular class data set for that particular class. That is what the implication is. Only your eigen values will change.
Okay. Eigenvalues will change. Okay.
Yeah. Yeah.
Yeah. Right.
Okay, fine. So
Yeah.
that is what the adiabatic theorem implementation we've done for classification approach as well. Now for the class of the trained data, we'll have eigenvector matrices and the range of the eigenvalue matrices within a particular class. This range, what we are talking about, ideally, if it is an adiabatic process, if it is the underlying probability distribution of your classical data set is following this adiabatic theorem setup, then only your eigenvector. So if you'll write right your Hamiltonian for every data in a particular class, then you'll SVD decompose that, right? SVD decompose that condition such that your eigenvector matrices will remain same for everything, but
Right.
only your eigenvalue matrices will change. Then it should be diagonal. Ideally,
Right.
it should be diagonal and it should change. But what happens actually for any data set or any other data set it will take into, since the degree is greater than like let's say 1, so that degree is coming to the picture here, or there might be other like implications of underlying probability distribution that we will have to look into, but that is reflected being the eigenvalue matrix is not diagonal in that case. If you have to exactly reproduce your Hamiltonian, right, the in between eigenvalue matrix whatever is there is not diagonalized, is not diagonal. Basically it implies that the adiabatic theorem is not an exact approximation for any data set. So that was
Okay.
yeah, for that particular class. So yeah, hope that point is clear, but still we are trying to like imply that. So how we'll imply that in terms of code, we'll look into using an ML approach. What we are trying to do in ML approach basically, for every classes data set, we are trying to find that mean Hamiltonian eigenvector matrices, as in the mean Hamiltonian, which will perturb which will perturb the eigenvalues of such that it can parameterize or it can reproduce the whole data set. Hope that you understand. Yeah.
Right.
Yeah. So eigenvector matrices will be same as the mean Hamiltonian, but the perturbing of the values that will essentially reproduce your whole classical data set. So whatever like problem statement was given to you, the parameterization of your classical data set, right? That is coming to the picture here. So basically you're parameterizing your classical data set for that particular class using adiabatic theorem, using basically the eigenvalues of that mean Hamiltonian. So how to find that mean Hamiltonian? We have used ML approach for that, and how it is implemented, we'll look into the code that later. Fine.
Yeah.
Okay. And now this plot is also taken in the picture. Like the mean eigenvalue plots are given to you. You can have a look at that at the code as well. Now this statement directly taken from the Wikipedia, so you can have a look at it. This is adiabatic theorem. It's given by Max Born and Fock in 1928. A physical system in its instantaneous eigenstate, if given perturbation is acting on it slowly enough, and if there is a gap between the eigenvalue and the rest of the Hamiltonian spectrum. Okay. Yeah. So, okay, if there is a gap between, okay, then the subsequent statement is not written or what? I yeah. If there is, and then there is no subsequent statement written. Okay, fine. So you can go have a look at the Wikipedia statement. So the first three lines are basically taken here. I don't know why I forgot to write the remaining statement. So yeah, basically if you look into it's the same statement. If you look into the top, it's instantaneous eigenstate if given the perturbation is acting slowly enough, and to the physical system. If like, let's consider a swinging bob, pendulum. So that pendulum, as in we are giving a disturbance slowly enough to it, such that its eigenstate, as in eigenvectors, are preserved. Only the eigenvalues change. And then if there is gap between the eigenvalues and the rest of the Hamiltonian spectrum, so that eigenvalues are changed. So in quantum mechanics, basically that levels of the eigenvalues are like changed.
Okay.
Yeah.
Okay.
Yeah. So we'll not go into the exact details. So you'll be going to exact details of quantum harmonic oscillator. So that was a thought process that we wanted to do that project to you as well. As in that is the next project of this, but we have not yet, you can say, implemented. We are not yet implemented that because we are having already like many tasks related to this.
Right. Right. Right.
Yeah. So hence, like we are assuming the changes in Hamiltonian of a particular class as the perturbation applied to the Hamiltonian slowly enough to preserve the eigenstate and change only the eigenvalues. Fine. So this one is clear. Yeah. So the next part of this, if you are clear on this, right? The next part of this, what it will be. Now what we are doing is basically perturbing your eigenvalues to parameterize your classical data set of that particular class. Next step for this, what it will be, you can parameterize or you can perturb your eigenvalues as well. And there is a separate perturbation theory for that. Right?
Okay.
Yeah. So, yeah. So that is your one of the tasks. So employing your perturbation theory here. So perturbation theory for your eigenvalues are like implemented in terms of weight vectors. How it is implemented in the code we'll go into. But the second stage for that is like you can apply a perturbation of higher orders to your eigenvalue.
Okay.
Yeah. Yeah. That only for eigenvalues you can implement. And for eigenvectors, we can skip for now. No need to perturb the eigenvectors as well. It will exactly reproduce your data set. It can. Yeah.
Okay.
Yeah.
Okay.
Because you're perturbing a data, but you have to parameterize it. What is the perturbation required for every case of that particular class? So let's say you have your Hamiltonian. You have your mean Hamiltonian. You have SPD decompose that into eigenvectors as an eigenvector matrices and eigenmatrix you have, right? Now you are perturbing both your eigen matrix as an eigenvalue matrix and eigenvector matrix. Both you're perturbing in the sense what you're doing is basically adding a coefficient multiplied by a higher order state as in higher order element of that. So for every element in the eigenvector matrices, if you consider, you're adding a term that is having a coefficient and that is having a variable associated with that variable will necessarily be your element what it is, as in you're adding a higher orders of the same elements in that, and that parameterization of that coefficient is basically what you can do later at the later stage. So that essentially implies perturbation theory.
Okay.
Yeah, so hope that point is clear. Yeah. Okay, fine. And this is nothing but your so this is what you are trying to do. H image within a particular class is equal to H class, this mean class what you are getting, as in keeping the eigenstate same and the mean eigenvalue matrix plus your perturbation what you're giving
Right.
to this, and this should produce all the Hamiltonians within a particular class.
Okay. Yeah. Okay.
Yeah, if your classical data set, as in quantum encoded classical data set, follows that adiabatic theorem here.
Okay.
Yeah, if it doesn't, we have to implement additional perturbations into the matrices, eigenvector matrices. That would have been your next project, but we'll not discuss that here. Fine. Then moving on, if the process of perturbation is fast, then the eigenvectors are not resolved, but the spatial probability density of the class remains unchanged. So this is what we are trying. So if the process of perturbation is fast, so what basically what we are trying to do here, if you take your image of your particular class, then the changes in that image, as in the changes in the probability distribution of from wherever that particular data is sampled from, the underlying probability distribution remains the same, right? And then basically that underlying probability distribution, the sampling is perturbation. Like that sampling is introduced to the perturbation here in your eigenvalue matrices. That is what you are trying to model here, basically. So hope this point is clear. Okay. Now,
Okay.
so we can also parameterize the Hamiltonian to nearest quantum systems. So how so once this is clear, like how to get that Hamiltonian from the classical data set, we can parameterize it to the nearest quantum systems. How exactly? Like we can write it terms of half into k into x cap square, x cap reference operator here, plus p cap square upon twice m. So you can write that in that terms. So as in you're assuming your Hamiltonian of that particular class to be a quantum harmonic oscillator here, and the parameterizer terms for that will be your p cap square matrices and your x cap square matrices, that and your k and that m, that will be your parametrizations of that particular class parameters. And this should satisfy this x cap and p cap should be Hermitian first of all, and it should satisfy a constraint of xp x cap p cap minus p cap x cap is equal to I h cross. So that can be one of the thing. Or the second thought process here is written here. So second thought process is what? Whatever Hamiltonian will be getting, you can plot the eigenvalue matrices of every Hamiltonian that will be getting. That every Hamiltonian's eigenvalue plot, what will be getting, you can try comparing the eigenvalue plot with this all systems, whatever Schrödinger's equations you have solved. And all these systems will be having E as a function of n, as in a number of quanta levels. So that plot you can compare and then try to figure out what is the system or the nearest quantum system from this, that parameterizing that can give us this set of eigenvalues. So that is again a research criteria, but again this is just like you can say we have not implemented that here, so you can skip for now. This is just a you can say a complete overview. The main task is already been explained to you. Fine. Then fine, cool. You can
Yes.
go over this if this is not implemented as well. Fine.
Yeah. Sure, sir.
Okay. Then we'll move on to the code.
Yeah.
So this is the end goal. If you look into this, this is the end goal. End goal is parameterization of the classical datasets underlying
Right.
probability distribution
Yes.
by
Right.
assigning a nearest physical quantum system to it. So basically, I'll just give you I'll just digress for a bit. Try to understand what I'm digressing. Let's say we have a classical data set, right? Let's say you're taking your MNIST data set, right?
Mhm.
That MNIST data set, whatever class labels are there, that
Mhm.
class labels, when you
Mhm.
are taking, right, when you're applying your neural network or whenever you're applying your any ML model, what ML model or neural network model does basically,
Mhm.
it tries to sample from the underlying probability distribution. So what your y is given the x. So p
Mhm.
of y given x, that is the probability that you're trying to model using a neural network or trying to model using a ML model, right?
Mhm.
Now, instead of a neural network model or instead of a ML model, we're
Mhm.
trying to model that probability distribution using a physical system. That physical system is nothing but it can be any nearest physical system, anharmonic quantum oscillator, harmonic oscillator, or any other system, free particle, delta function, like any other things. Okay,
Okay.
so hope that point is clear.
Right.
And this is also there. The second way is time independent dependent perturbations.
Mhm.
So yeah. So one thing also you can try is whatever Hamilton matrix you are getting, right?
Mhm.
Those Hamilton matrix for a particular class. Let's say you are having 5,000 samples in a particular class, and Hamilton you are writing. That Hamilton can be written as a kinetic energy plus potential energy sum. So basically, the
Right.
diagonal elements will be your potential energies, and the off diagonal elements will be your kinetic energies. And
Right.
that, what we are saying is that you can evolve, time evolve, as in you can apply a time evolution to that Hamiltonian to
Mhm.
get the next Hamiltonian in the same data set. So if you
Okay.
will, so what we're trying to basically say, if you'll arrange your data set into the orders of increasing Frobenius norms of your Hamiltonians, from starting from lesser Frobenius norm to higher Frobenius norms,
Mhm.
then the highest Frobenius norm and the lowest Frobenius norm, whatever that is, you can model that as a evolution, time evolution of your Hamiltonian matrix.
Okay. Okay.
Yeah. So that can also be thought about. Time evolution, by what exactly we mean here, whatever values you're having in the elements, right? That
Mhm.
elements values, how it is changing with respect to time. That function you can model. And essentially you can get a single Hamiltonian, which you can write as a function of t
Mhm.
into mean Hamiltonian. That will parameterize your entire data set for that particular class. And then you'll get all these Hamiltonian for the next classes. So basically this mean Hamiltonian into that function of time will also be a second way of parameterizing your classical data. So there are like five, six, seven. There are more ways. Like this is all
Mhm.
like we have thought of physically. So this is novel implementation physically in Hayama quantum here, but
Mhm.
like we are not yet implemented it. So your task remains of the only about thing. Fine. Well, we'll move on to the code. Could you please share your screen?
Yeah. Yeah. Sure, sir. Yes. Is my screen visible?
Yes.
Yeah.
Yeah. So yeah. Could you press Control B?
Control P.
Yeah. Okay, control B it is, right? As in you have to remove this explorer part, like we can visible.
Okay. 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 Okay.
Is control B only,
Yeah.
right?
Yeah.
Shortcut, I don't know. Okay, yeah. So this is task is written here.
Mhm.
You can go through that.
Right.
So interns type task to implement, as in we are not thought about which one, which intent to be which project. So we are just written intern. The
Right.
various given density matrix encodings in the previous code as well,
Mhm.
uh, as the doc and not the classification result, which gives the best classification accuracy, grasp the concept of the adiabatic quantum combination. So whatever ways of getting that Hermitian matrix, right, that are
Mhm.
implemented in your novel density matrix encoding for the same classical data set, you can try incorporating that here as well. As in for
Mhm.
demonstration purposes, what we are tried here is basically A plus A transpose by 2, I think, or A into A transpose by 2.
Yeah. Yeah. Yes.
Okay. Yeah, I think so. Your screen is yeah, yeah, fine. There is some lag in the connection. So yeah, okay, fine. Now this step is already been discussed in your first day as well, and today also we discussed it with when I was giving a demo with, for Tulsi, right? Some
Yes.
part of
Yes.
it is feature. So this code you can go through. Yeah,
Yes.
yeah. So could you kindly go above? So only three, 4 points we'll discuss. So this Hermitian matrix, right? What you have gotten.
Mhm.
This
Mhm.
is for test. Yeah. So above process is like what we have done basically. The first process is this normalized stage images, like we have normalized that into the
Right.
vector format, and
Mm-hmm.
then okay, no. So here we have kept the images as it is.
Right.
Okay, then we have reshaped that. Okay, now okay, just a sec. So here, okay, fine. So here we have implemented another method. We have not implemented A into A transpose by 2. I
Yeah,
thought
yeah.
like this
Actually,
was,
I guess, yeah, yeah.
yeah.
I
So we
guess
have
you have used,
implement we
there
have
is a one
implemented
function.
no, that function is for density matrix. It's not here. That's what I was like little bit confused about, because this we have implemented outer np dot outer of n comma
Ha.
m.
Yes, yes, yes,
Yeah, so
yes.
this is
Ha.
nothing but your, so I thought like particularly we had implemented A plus A transpose by 2 here. I thought for
Yeah.
your case, but no, it was like this case. You can try
Mhm.
implementing other techniques as well, right? So instead of
Right.
this, you can just define m plus m, no, not m plus n transpose by 2. That will be given there. You don't have to reshape here.
Mm-hmm.
This reshape, right? 10,000 comma 64. Don't reshape it. Keep
Okay.
the 8 comma 8 as it is, 1000 comma 8
Right.
comma 8.
Mm-hmm.
Then what you can do is for every 8 comma 8, you can do that A plus A transpose by 2. And
Okay.
normalize that. That will be your Hamiltonian matrix. Or you can take A into A transpose by 2 as well. Or you can try incorporating other density matrix techniques what we'll discuss of getting that Hermitian matrix, right?
Okay.
Okay, fine, cool. Hope that one. This is for test, and the test and the train implementation should be coherent. Okay.
Right. Yes.
What?
Right.
Yeah. Cool.
Okay. Uh, okay.
Yeah. Any queries in this?
Uh, so like in this whole code, like how have we computed the Hermitian matrices then if we have not used that A plus A transpose by 2? Okay,
So
so
this
we have
is,
used that outer product.
yeah, outer product, the third technique.
Okay, okay.
NP
Oh,
dot outer m comma m, right? Yeah.
yeah, yeah, yeah. Sure, got it.
Yeah.
Yeah. Okay. But I can also implement it that with A plus A transpose by 2 or the other two methods, right?
Yeah. Other 4 5 methods all discussed in novel density matrix or the
Yeah, yeah.
document as well. Yeah.
Okay, okay, okay.
Yeah. But the other methods, main focus should be on that unitary.
Right,
Unitary to
right,
Hamiltonian conversion, because that will be your exact Hamiltonian.
right, 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 right.
Yeah. Now this code is basically getting your so we have implemented that SPD transpose. So let's go code line by line. So this is nothing but the function that we have implemented, and we have
Mhm.
passed in the arguments the Hamiltonians. So what this function basically is, it will calculate all the eigenvalues and the eigenvector matrices. So that is what this function is for.
Right.
So if you look into the function, the n is assigned a value of
Mhm.
your like whatever image matrix you will be having. And so here it's outer product, right? So
Right.
that so after that Hamiltonian, so whatever shape is, you'll be having that as an n value, and
Mhm.
then we are initiating your eigenvalues and eigenvector matrices to
Mhm.
be like empty matrices here having these dimensions, and the total will
Right.
be your number of samples whatever there are.
Right.
And yeah, so and this is a check is what we implemented here. So this A and C are nothing but eigenvector matrices, and this
Mhm.
B is nothing but your eigen value matrix here. Okay, fine.
Right.
And this is Hermitian is implemented just to check whether the Hamiltonians are like you can say Hamiltonian minus Hamiltonian dagger is equal to 0 or not. So that
Mhm.
np dot all close is, but this np dot all close again is what you have to check online is what is the level of error this implements.
Ah.
I think it's 10 raised to minus 10. So
Yes, yes, yes.
if it is below 10 raised to minus 10, right, then
Mhm.
it will show that it is not an Hermitian. As in, if the error is above 10 raised to minus 10,
Mhm.
it will show like it is Hermitian.
Right, right, right,
Yeah, it will
right.
identify that as a Hermitian. But
Mm.
if your error in the Hamiltonian itself, as in the elements is of the range 10 raised to minus 2, 10 raised to minus 13, it cannot identify. So better to introduce if else statement here instead of this. That will also be done. Okay, fine. Yeah. Now this is nothing but the eigenvalues and the eigenvector matrices. Fine.
Mhm. Right.
Yeah. So you decompose that. So you just introduce the eigenfunction here. Into the edge, and then fine. So you are returning all that, and then for every like matrix you are taken that normalized Hermitian digit matrices in the trend data set, you are getting these 3 matrices. So eigenvector 3 eigenvector uh, 2 matrices, and that the eigenvalue matrix. So hope that point is clear,
Yes,
and the
yes.
similar you can do for test data as well. Okay.
Right, right.
Okay. Now so this is your approach one,
Mhm.
in which you are parameterizing the classical data set. So how you are parameterizing the classical data set, which you already discussed using adiabatic theorem, basically is
Mhm.
whatever changes are in your class, particular class data sets Hamiltonian, those all changes will be done in your eigenvalue matrices, and your eigenvector matrices will be same. But how to calculate that mean eigenvector matrices and that mean eigenvalue matrix, that is what you have to find. So that mean eigenvector matrices is found by ML technique here. What you can do is
Mhm.
directly take a statistical mean of all the Hamiltonian. That will also work fine. But we
Okay.
have implemented a better technique from that. But yeah, so how this is better from that, like we'll go over the code. So this is nothing but a matrix model class that we initiated, and
Mhm.
then a number of classes, how many there are, and those many number of eigenvectors and those many number of eigenvalues is what you have to find, right? So
Right,
this,
right, right, right.
so for every class there will be one eigenvector, and then one eigenvector matrix. So that
Mhm.
is why 10 comma 64 comma 64, because your outer productive size is 64 comma 64 of matrix. So that is what is initiated here.
Mhm.
Similarly for eigenvalues, it will be 64 only. But what you can do is np dot diagonalize here or torch dot diagonalize here, and you can construct it. So that is implemented at later step. So no need to do here, but because the
Mhm.
parameters in that case also will remain to be 64. So those are just initiated here. Fine. And then make unitary constraint is imposed. Okay.
Mhm.
So okay.
Yes, buddy.
Yeah. So why we are implementing make unitary constraint here? Because whatever eigenvectors you will be having, right? Those
Mhm.
eigenvectors should be unitary for our case. Why they
Okay.
should be unitary? Because that is what the sole basis of SVD decomposition is.
Right.
Unitary constraints underlying concept is what? The columns and the rows should be orthonormal to each other. So that is the sole constraint there. So that constraint we have taken here. So that constraint also belong to unitary class. That is why it's written define make unitary, in which case whatever eigenvector matrices you are initiated, right? Those initiate eigenvector matrices, you are SVD decomposing that and then multiplying the eigenvector matrices of that. So hope that one is clear. Eigenvector matrix you are again decomposing using SVD technique and then multiplying the eigenvector matrices of that to initiate your eigenvector matrix to be a normalized orthonormal matrix as in a unitary matrix. Hope that point is clear. So this make unitary constraint is for that. So
Mhm.
for both the eigenvector vector matrices is done. So this unitary constraint. Hope that point is clear. So
Right,
now
right.
get Hamiltonians, what this basically does is uh, okay, so diagonalize. So we are multi. So what this basically does, this unitary is nothing but now your eigenvector matrices, right? This
Right, right.
eigenvector matrices, and then this is your so whatever eigenvalues you have, that
Mhm.
eigenvalues you're diagonalizing it again, or diagonalizing it to
Mhm.
convert it into a matrix kind of setting, because you initiated the parameters in the form of just 64 you initiated, right? So
Right, right,
that
right.
you're diagonalizing and that multiplying that diagonal like unitary diagonalizing unitary, and that
Right.
transpose dot transpose that conjugate dot transpose is done here, because whatever second eigenvector matrix you'll be having, that will be a conjugate transpose of the first one.
Right, right.
Yeah,
Okay.
so that is what is done here in the get Hamiltonians. Once that
Mhm.
get Hamilton is same, so instead of doing this, what you can do is get Hamilton itself, you can write a forward method there, because the same thing is written here.
Right, right, right.
Yeah, instead of defining both functions, you can write define forward comma self in that past self argument. Fine. Then
Oh.
in the combined loss, what you're trying to do is uh, so whatever output you'll be getting from here, right? This Hamiltonians.
Mhm.
So these Hamiltonians should be same as your target Hamiltonian. So yeah, mm, just let me try to recall. Yeah, so here what will be your target states? Here what will be your target states? So this will be your output, right? What will be your output now? Output will be of the shape of a 10 comma so no, so yeah, so you're taking mean for that particular class. So just give me a sec. Output you're taking, just go ahead above. Yeah, fine, this is fine. 10 comma 64 comma 64, you're taking Hamiltonian of that. Okay, fine. The target states 10 comma 100 comma 64 comma 64. Yeah. Now it's clear. Yeah. So like what you're basically doing here,
Mhm.
yeah. So yeah, it was quite a while back. So what you're basically doing here is you have your target state defined, right? I mean, you have your target state defined in the sense like
Mhm.
whatever output you'll be having, that should
Mhm.
be close to. So you're taken 1,000 to be data set here. As in, if you
Right.
look into, you're taken 1,000 comma 64 comma 64 to be a data set. As in, each class has your 100 samples as your
Mhm.
like Hamiltonian. As in, particular class has 100 samples as your Hamiltonian. So
Right.
what this target.view does is basically reshapes it to 10 a particular class 100 comma 64 comma 64, and
Mhm.
that forms your loss function. As in, this target state will look into what is passed in the argument of training loop. Can you go below? Yeah. So this, this training loop will look into this target matrices are nothing but your output matrices. These are
Oh.
nothing but your output matrices. As in, after training your
Mhm.
model just has your 10 eigenvector matrices and 10 eigenvalue matrices, right?
Mhm.
10 eigenvector matrices, 10 eigenvalue matrices, and then you'll be getting just your 10 Hamiltonian matrices, right? That is
Mhm.
just your output. But that single output of that particular class should be near to, or you can say centered of, all
Mhm.
the possible Hamiltonians. So that is what we want to incorporate in a combined loss. So that is where the target should be this, and your output should be like the output what you'll be getting from the model. So hope that point is clear. So can you
Right.
go above? Yeah, yeah. So this is nothing but okay. This is initiated as a tensor. Fine. And could you go above this? Yeah. So here, yeah. So this you are taking target dot view 10 10 comma 100 comma 64 comma 64, right? And
Mhm.
then you're reshaping your output what you'll be getting from above to be in the format of this 10 comma 64 comma 64. That will be your output here. 10 comma
Okay.
64 comma 64, because for uh, every class you'll be having just a single eigenvector matrix and eigenvalue matrix, right? So
Right. Right.
that, yeah, so instead of 100 you'll be just having single. So and then you're subtracting it from every like target matrices. So yeah, and this yeah, so you can try incorporating a for loop here as well, or just a single line written here as well, also separate, because in the dimension it is mentioned 2 comma 3. But
Mhm.
what you can do is you can introduce a for loop as well for
Okay.
every state in your target.
Mhm.
Like for every state in your target, that 100 index is what I'm talking about.
Mhm.
If that belongs to your class J, you have to
Mhm.
introduce two for loops, and then the subsequent classes subtraction you can do. That will be a loss, and then add that loss. So I can
Okay.
write it down. And I hope that point is clear. Two for loops you
Right.
can
Right.
introduce, or you can keep this implementation as a tor dot mean of. Then finally
Mhm.
also you have to take mean only of that implementation. And instead of doing it in for loop, this is better because
Okay.
this is in vectorized form. So it will be a
Mhm.
faster execution of that combined loss. So
Mhm.
hope that concept is clear. What
Right. Right.
combined loss basically want? So what
Yes.
combined loss basically want is every Hamiltonian of that particular class should
Mhm.
be near to your Hamiltonian what you will be getting for that particular class, what you will be
Mhm.
modeling for that particular class.
Right.
So after getting that Hamiltonian for that particular class from this ML, so that will be essentially from this accurately will be centroid. So instead of
Mhm.
following all this, what you can directly take is mean. That will be better. So
Right.
that's
Okay.
an option. Yeah.
Yeah.
Okay, fine. So that is nothing but done here, and this is your training loop. So hope that point is clear.
Yes.
Yeah. Uh, yeah. Now this is similarly done for your. Okay, fine. Yeah, these are just the printed section, and the
Printed
below is
set.
similarly done for your test data set. So
Right.
one now you approach we have tried implementing below.
Mhm.
So this is nothing but the implementation, nearest neighbor implementation. Can you go above? Yeah. This is a nearest neighbor implementation, as in
Okay.
the another approach of implementation of inference from what you're
Mhm.
getting, right? So based on
Mhm.
what your trained eigenvalues and eigenvectors you have, or trained 10 Hamiltons you have, how we can infer whether that test data set, test Hamiltonian, belongs to this class or not. So what you
Okay.
can directly do is implement a KNN. So this is a form of KNN what you're trying to implement, as in
Okay.
find the distance,
Mhm.
Euclidean distance of that matrix with all the 10 matrices, and then take the uh, smallest
Minimum.
values of that, smallest value of that. So argument mean is
Okay.
taken, right? The smallest
Right.
value of
Right.
that. Yeah. So
Okay.
that is
Okay.
okay. So this is an I approach. Like there
Mhm.
will be better approaches, which is coded in the later section. If we go into below.
Okay.
So this is again like just a plotting of whatever eigenvalues we have gotten
Okay.
from the
Okay.
model. From the model,
Mhm.
yeah,
Mhm.
for every class.
Right. Okay.
Yeah. Now this is the second. Okay. Okay. Could you go above? Yeah. So whatever code was implemented above, right? The
Mhm.
same inference on the test data now using ML pipeline will decompose each test data sets, data points Hamiltonians using 10 eigenvector matrix already trained previously, and diagonal eigenvalue diagonal matrices parameterizable for
Mhm.
each data set. Each class of the test data will be found using ML pipeline to reduce the reconstruction of the test Hamiltonian, and the
Mhm.
reconstruct Hamiltonian we using the okay. I'm just reading this.
Right. 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 Yes. Yes. Yes.
Yeah, using eigen equation and then plot the eigenvalues. Plot as per test data is follow the trained data ideal eigenvalues probability distribution and which is closer. Okay, fine. I don't recall, but let's see below. Like I'll be
Okay.
able to recall when I see the code.
I guess this is the
Yeah,
same code.
yeah, but yeah, same code above. The implementation at the end, what you're getting for inferencing, right? That is only changed. Yeah.
Okay. Okay.
Okay. Okay. I actually don't recall this. Just give me a sec. Okay. Okay. Yeah. So could you go below?
Okay.
Okay. So fine. So this is fine. Batch decompose is done. I remember like the same code was there as in what we so same code is used for training as in the same Hamilton which you got, right? And
Mhm.
here the second implementation was just we are trying to brain rack different ways as in different metrics for getting inference on the test data.
Oh.
So yeah, so this code was written a while back, so I'll have to go into details of that. But if you look into like
Mhm.
various metrics of the classification accuracies are like implemented here, just metrics. And the prior code of getting that eigenvector matrices remain the same. Eigenvector,
Yeah.
eigenvalue matrix. Yeah,
Right. Right.
and this is only implemented for inference purpose on the test data. So yeah,
Okay. Okay.
now this is subclass 2. This is a new implementation.
Hmm.
Yeah, and this in this case we are introducing perturbation.
Okay.
So we are introducing perturbation. How exactly?
Hmm.
Like we are multiplying our eigenvector matrices with another vector.
Okay.
Yeah. So as in we have to perturb our eigenvalues, right?
Hmm.
To reproduce the whole data set. So we
Hmm.
are multiplying your eigenvalues with
Hmm.
a weight vector that is parameterizable.
Hmm. Okay.
Okay. Okay, fine. So this remains the same. Self or eigenvector cell dot base eigenvalues remain the same. Self weights upper like over. So self weights. This is a new parameter that is defined.
Yeah.
And
Okay.
so what we are trying to basically do here is so let me share my screen. Yeah. So is my screen visible?
Yes, sir.
So this is your mean Hamiltonian, as in mean Hamiltonian, and this is your mean eigenvalue matrix, right?
Okay.
Mean
Right.
eigenvalue matrix. Yeah. Now keeping this both as same, you're
Hmm.
trying to perturb your mean eigenvalues of that particular class of that particular class
Hmm.
using a multiplication. So you are multiplying
Hmm.
this. Let's say now since this is a diagonal, you can consider this as a vector itself. You are
Okay.
multiplying this with this weight vector.
Okay.
Yeah, multiplying this with a weight vector.
Hmm.
Yeah, that's it. So once
Okay.
you are multiplying this with the weight vector, you will get a new eigenvalue set. And
Hmm.
this eigenvectors are defined for every data, every
Hmm.
data point.
Right.
So how many data points you have, right? For in that particular class,
Hmm.
as in 1,000 you will be having.
Right.
Particular class you will be having 100, and total you will be having 1,000. For
Right.
every 1,000 vector, you will be initiating this, and then
Okay.
multiplying with your mean eigenvalue matrix.
Hmm.
And after multiplying, as per our theorem, it should reproduce your Hamiltonian.
Hmm.
It should reproduce your Hamiltonian as in the Hamiltonian of actual data. This is your mean
Hmm.
Hamiltonian. It should
Right.
reproduce the Hamiltonian of your actual data. So that
Hmm.
is what the adiabatic theorem was. So we are just
Okay.
limited to perturbation of your eigenvalue matrix. And so instead of this perturbation, what you can do is
Hmm.
this E1, E2 up to E63 you will be having, right? So this E
Hmm.
are nothing but the energies. So
Right.
this and the mean of that will be a ground state. Okay, anyways. But this, if you look into, and if you introduce a lambda into V kind of setting here, that is nothing but another kind of perturbation that you can introduce. So V square
Okay.
plus, yeah, lambda 0, lambda 1, lambda 2. These coefficients I was talking about earlier. So this lambda 0, lambda 1, lambda 2 will be your coefficients, and this will
Right.
be your higher order perturbation, and this will
Okay.
be your non-linear perturbation. So you
Hmm.
can try to model your eigenvalues based on this as well, but we are limited here to your to your weight matrix. So weight vectors. So you are
Okay.
trying to model that perturbation using weight vectors. So you can try to model using other approaches. That will be a task for this. As in
Okay.
you can incorporate a nonlinear equation and try to parameterize this lambda values what they are, and try to exactly reproduce the data set, classical data set of that
Okay.
1,000, 64, 64. Yeah.
Okay.
Yeah, fine. So that will be a task, and you can incorporate. So this is a higher order nonlinearity that you incorporate. You can try incorporating perturbation theory.
Okay.
Perturbation
Okay.
theory for eigen. So you have to go through perturbation theory, particularly for eigenvalues.
Okay. Okay.
Yeah, fine.
Yes. Yes.
Cool.
Yes.
Yeah. So fine. Could you please kindly share your screen?
Yes. I guess I'm sharing.
So so you're okay. You're seeing my screen, right? Priorly.
Yes, sir. Yes, sir.
Okay, cool. Okay. So
Sir, like top, bottom. I guess you can stop sharing your screen so that my screen. Yeah.
okay. Yeah. 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 Yeah.
Yeah.
Okay, yeah, so same code is implemented here. The weights are initiated here.
Right.
And then, yeah, so same code, get Hamilton, make unitary, that code remains the same. If
Mhm.
you'll find just a multiplication is done. So if you go
Right.
into a convolution operation is done here, right? Self
Mhm.
weight of C class. So you initiated of the shape. So if you look into how the weight vectors are initiated, those are
Mhm.
initiated number of classes, comma 100, comma 64, comma 64. So this C
Right.
basically implies how many in which class you are, and
Right.
multiplying a base eigenvalue of that class
Mhm.
that which initiated earlier. That is what the only change is done here. Baki everything remains the same. And here, so for doing that exact reproducibility,
Mhm.
ideally, what can be done is directly take that mean Hamiltonian of that particular class, decompose it, and then initiate. Don't take eigenvalues and eigenvectors as the parameterizable sections here. But for
Mhm.
getting that accurate, whether we can model exactly our system, for getting that accuracy, what we are trying to do is again parameterize the eigenvectors and eigenvalues. Again, introduce those as parameters. Those will also be trained by backpropagation of the loss function. So hope that point is clear.
Okay.
Yeah. Yeah. So the same loss function is implemented, and the remaining loops remains exactly the same. Here only the change is you are finding a weight matrix for every class. Every
Class.
class is data.
Right. Right.
Yeah. Fine. And then once you get that, for every class, you will be getting your mean Hamiltonian,
Mhm.
and you can multiply your weight vector with
Mhm.
that Hamiltonian per se. Multiply directly that weight vector with that Hamiltonian, or you can SVT decompose that Hamiltonian and multiply your weight vector with the eigenvalues of that Hamiltonian, and
Mhm.
then find the Frobenius norm of your gotten Hamiltonian with the actual Hamiltonian of that data set. That should be
Okay.
minimum here.
Okay. Okay.
Yeah, parametrization of the classical data set. That is what you're trying to do, and then you can again implement a KNN, a nearest neighbor algorithm for like finding, as in for inferencing on the test data.
Okay. Okay.
So whatever 10 this you have, right?
Mhm.
10 classic 10 matrices you have, Hamilton matrices you have.
Mhm.
no, now in this case, you'll be having your all the 1,000
Thousand.
parameters, parameters Hamilton matrices. In this
Okay,
case,
okay.
yeah. So all the matrices you will be having from the model, right?
Hmm.
Parameterized, but they are parameters. Parameters on what? On the perturbed eigenvalues.
Okay.
Perturbed eigenvalues, they are parameters on. So you will be having a 1,000, 64, values.
Hmm.
That values you can implement your KNN. As in,
Okay.
whatever test vector you have, you
Hmm.
can try like inferencing the norm for
Hmm.
every classes 100 vectors with that test vector what you have. So what you will be having are 100 classes, 100 values for a
Right.
particular class.
Hmm.
And so you can like deploy various algorithms here, like max voting or other algorithms.
Hmm.
KNN algorithm also you can implement
Hmm.
to find which class does this belong to. This will be accurately, like this will be better than the previous accuracy because you have more samples. As in, you can deploy your bagging algorithm, boosting algorithm, stacking algorithm for
Hmm.
finding like which which class does exactly a test vector belong to, because you have more
Okay.
number of train samples, right? As in, you have more
Hmm.
number of your 100 compared to previous one. So hope
Right.
that point is clear. Yeah.
Right.
So that
Okay.
can be done. So this is done. Voting accuracy is implemented. Maximum voting is implemented here.
Hmm.
So
Okay.
yeah, you can try going to that code. Uh, yeah, and accuracy of this compared to the previous one is better.
Okay.
Yeah, and what you can try implementing here is your another task will implement KNN and other majority like voting majority already implemented. You
Hmm.
can try incorporating KNN with nearest neighbor taking as 5, and then you can try implementing various bagging and boosting techniques.
Okay.
Yeah, on this. Fine.
Hmm.
So these are again the plots of the eigenvalues. These are not in arranged in like increase amount. That's why it's showing like this. We go into
Okay.
billing, like those are arranged in increasing order. No, yeah, these are arranged in increasing order.
Okay.
Yeah, the same eigenvalues plot. Fine.
Hmm.
Yeah. Now this is the inference
Hmm.
section, and these are the points written there. You can go through the code there.
Right.
Fine.
Okay. Hmm.
And complete implementation of the code along the inference of subcase 2. So above code can be used for visualization of the train data eigenvalues.
Hmm.
Fine. So same code is taken here as well. So if you go
Right.
into build, yeah,
Okay.
yeah, yeah. Okay. Generate Hamilton. So this section what you implemented, right? So we were trying to implement other like distance metrics
Okay.
apart from, yeah. So same what you have done right in the second block, code block. After discussing your basic first code block of
Hmm.
your implementation, first method. After that, the same code block were taken in the next method as well.
Hmm.
Similarly, this is the implementation of the above method itself, but here you incorporate different distinct metrics, distance metrics.
Okay.
So you can
Okay.
try, yeah, for just getting that inference correct. The
Okay.
implementation and what we discuss exactly remains the same as the
Okay.
above code block.
Okay.
Yeah, only the distance metrics for inferencing is changed, whether we get that subsequent increase in accuracy or not. That's it.
Okay.
Yeah, fine.
Yeah.
Yeah. So various kind of metrics are used here. Like
Hmm.
you can go through. So
Yes.
it doesn't give any improvement in accuracy per se. Like
Oh.
Frobenius norm like is already implemented.
Hmm.
So you can go through. Like yeah, fine.
Yeah.
And these are your tasks written.
Okay.
So hope this like discussion is clear. If you have any
Yes.
doubts, you can ping us
Yes,
also.
actually, yeah. Actually, I have started implementing this notebook as well as the other common task, that is amplitude encoding. So yeah, I
Okay.
am doing both of them parallelly. Yeah,
Okay.
so like I am very like the before like the early part of code I'm very clear. Like I have completed up to this part, I guess. Mm, wait a minute, sir. Where is that thing? Yeah, so I have completed up to this. So basically here at the bottom you have wrote that basically here the eigenvalue spectras you have done. So what I'm trying is I'm trying to train a neural network model on these eigenvalue spectras, and then I'm giving them the text data from the MNIST dataset and seeing whether that model is able to predict the label of that image correctly. I'm trying that too.
Okay.
Yeah.
Okay. So Okay, fine. So what? Okay. But huh, so you are taking so but okay, you are training a model just on your 10 matrices, this 10 eigenvalue matrices and 10 feature spaces. That's it what you're trying to say? But it will
Yes.
give an average accuracy than it will. Then you will train neural network model will just give a 67% accuracy in that case. Because this
Okay.
will be a nearly a centroid of that, right? So this will be
Mhm.
similar to your average of the Hamiltonian.
Okay, okay, okay.
So I think we have implemented that in case of novel density matrix encoding as well.
Yeah, 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 yeah. Okay.
So, like, you can try thinking or brain racking from your end as well. But primary
Mhm.
focus should be on the task that we are discussing in this section and the task written there. So,
Yeah.
it is good that you came up with the implementation of implementing a neural network conditioned or the inputs will be the
Mhm.
eigenvalues of the 10 classes which are like modeled here.
Mhm.
But this will give a roughly 67% accuracy. So, yeah.
Okay, 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 okay.
So,
Yeah, yeah.
yeah. Cool. So, yeah. Any queries? Further queries from your end?
No, not uh, not now, but yeah, we will. I will ping you and Britain, sir.
Sure, sure, sure.
Yeah, yeah,
Cool then. So, yeah.
yeah, yeah.
Thanks.
Thank you, sir.
Sure. Thanks.